Welcome to Integrated Math 3. On this episode, Stevenson will demonstrate rewriting radicals is one aspect of dealing with radical expressions. Another one is called extracting roots. So an extracting root means simplifying out a radical. Now let's do a very quick review. This is our parent square root function. Remember, its domain is all positive numbers and 0. Okay? This is the cube root function. Its domain is all real numbers. It has no restrictions. How does this help us? Well, whenever you extract a root, or in other words, you complete a radical, okay, you complete the index, you're going to have two options in how you write this. Here's what you need to know. Whenever the index and the exponent are exactly the same, and remember, the index and the radical can be, the exponent can be on the inside or the outside of the radical. Okay, that's why I wrote it 2 times. When those match, then the root gets extracted. But here's the problem. If your index is even, then when you extract your root, you need to ensure that the result stays positive. So you may need to put absolute values around it. And that comes from the basis of the square root function and the fact that its domain can only be positive numbers and 0. However, if your index is odd, then there's no restriction when you simplify it. And the reason is because if you look at cube roots here, or any odd index, the domain is going to be all real numbers. There's no restrictions. So what does this look like in practice? Notice my index is 2. Now they match, don't they? What this means is I really have x squared to the power of 1/2. Well, what is 2 times 1/2? That's 2 over 2, which is 1 whole. So notice it simplifies to x to the power of 1. Here's the problem though. My index is even, which means I must ensure all of these numbers are positive numbers. Well, let's think about this. This is x to the power of 1. That's the identity function. Do you remember what that looks like? It's one of our parent functions. Could this ever be negative? Yes. So what we have to do is we have to put absolute values around it to ensure it only stays positive. Let's look at the next one. This is the cube root of x cubed. Well, what's 3 times 1/3? It's again 1 whole. So this is x to the power of 1. Now, do we need absolute values here? Well, what was the index? Is it odd or even? Well, the index is odd. So what that means is there's no protections needed. It can be any number, positive or negative. So this is our answer. Let's keep going. This is the square root of x to the power of 4. So this really is, the index is 2. So if we rewrite this, it would look like this. What's 4 times 1/2? It equals 2. So this is really x squared. Okay, do we need absolute values here? Well, my index is even, and according to this, I must ensure that all of the outputs are positive. Well, let's look at this graph though. This is x squared. This is our parent quadratic function. Is it possible for this ever to be negative? No. The range of this is always positive. It's 0 to positive infinity. So we don't have to put absolute values on this because this function already guarantees it'll only be positive. Now, if you still put absolute values around it, you could. It's not wrong, but it's highly unnecessary. So, when you look at these 2 examples here, why is it that the identity function needed absolute value but the quadratic didn't? Look at the range. The range of the identity function is all real numbers, so we had to ensure we only had the positives. The range of x squared was actually 0 to positive infinity. It's already restricting itself, so we're safe. Let's look at the last one. First I'm going to do is rewrite this. Now, what's 10 divided by 5? So it reduces to x squared. Now, my index is odd, so I don't have to worry about any restrictions. So this is my final answer.